Welcome to GDC 2021. It's great to be here presenting virtually. My name is Brian Colwell, and I'll be presenting today on using non-functional testing to guide game, user interface, backend, and voice interface development. So what is non-functional testing? There are really two types of testing. We have our traditional functional tests, and we have non-functional tests. So functional tests are defined in terms of pass-fail on input and outputs. So whether for some inputs, the system passed or failed. Non-functional tests are defined in terms of actions, scores, and baselines. So for functional tests within some reasonable definition of sample size, and eventually, we're testing that for the same inputs, the app eventually behaves in the same way. Test over test. So this is your core functionality. Is the app playable? Is the app broken? With non-functional tests, with as many samples as possible for some action of the app or backend, what we're looking at is how does the performance, the quality, the usability, the reliability compare to a target baseline? And so why do non-functional testing? Your team is probably already doing some type of functional testing, whether manually or automated. So why take the investment and build out additional non-functional testing? The main reason why you want to add non-functional testing to the way that you develop is because as you build and scale, you want to make sure that your key product areas continually get faster, more reliable, and a better experience. So these are really hard to test with functional tests. But when you look at the reviews coming off of the App Store, the Play Store, game stores, a lot of the feedback that comes underneath a 5-star or a 3-star review really speaks to the non-functional characteristics. Was the app fast? Was the app reliable? And were there regressions, for example, with the latest release? And this is what I want to talk today about is how do you set up a framework for your team to implement non-functional testing as part of your process. So how do you get there? How do you continually get faster, more reliable, and a better experience with your app? The key is to build out a framework within your development process that creates a safety net using data to catch non-functional regressions. And the real key to implementing non-functional testing is data. So getting the data that you need to make these non-functional regression decisions. So getting started is actually not that hard. You can start with what you have. You probably have a lot of data sources already in your development process that you can tap into to implement non-functional testing. So manual functional tests and automated functional tests can be a great source of data. These are running tests consistently for every build before it goes out. And you can really augment these tests to create data that you can use to do non-functional testing. Also, end users can be a great source of data for non-functional testing. You can look at some of the data coming from the field to make decisions on regressions and how the application is changing. In addition to the testing team, which is running your functional tests, there are some other skills you'll need to implement to actually start doing non-functional testing. You need to start integrating some of your data team skills and your product engineering team skills. So non-functional testing is really a collaboration across multiple teams. And we'll go into that in this talk, how you can structure that as part of your development framework to actually build out as part of your project team, non-functional testing as a skill. So the ultimate goal of non-functional testing is to create a regression safety net, starting with at the very top, raw data that you're collecting as part of your functional tests to your end users. Using that raw data, the first step to starting to implement non-functional tests is to identify hotspots in that raw data where you think there could be improvements. So for example, on the initial load, on searching, on navigating the game menus, on the gameplay itself, there are key areas that you think are critical for your game that you can start identifying where do you want to focus with your non-functional tests. Once you've identified those areas, you want to start looking at how do you measure specific questions that are relevant for your game or your app in those areas versus a baseline. And so this is really where your team has to discuss internally, what do you consider to be a good baseline? Is it a total time to accomplish the goal? Is it versus peers in the same space? Is it versus your own goals of what you want your game to perform? And so this is really specific to your game. How do you define these baselines? How do you quantify it? And we'll go into some examples of how to do this later in the presentation. Once you've identified those specific questions, then you want to track those specific questions and those quantities as you iterate. So every time you publish a new version, every time in production, at different times of day, or if you publish your game backend to different regions, you want to be measuring these. At every time you make a change, you want to measure these questions, because that's what we're going to start using these questions to make decisions about. Whenever a new version goes out, is it getting statistically worse for these questions than the previous versions? Also at different times of day or different backends or different locations around the world, is these non-functional metrics getting worse? And if they are, that's a red alert. This is a regression. And so your team, to continually improve, your team has to really stop here and really take this seriously. If something's regressing, you need to bring it back to the baseline before you move forward. Otherwise, you're going to be accumulating performance debt or usability debt. If there's no statistical difference versus the baseline, then congratulations, you've made an improvement to your non-functional behavior. And this is moving you continuously towards a better, more usable app, a more performant app, an app that's getting higher ratings. And so once you've achieved that baseline, you can actually pivot and ask more questions. So you have this in your pocket, it's being measured every build, and you can actually start asking more questions. So this safety net repeats from the top once you've achieved an improvement in your non-functional behavior, and you can start looking at the next areas that are most important to your game or application. So following this framework is a proven way for any team to continually get faster, more reliable, better experience. And following this framework results in, over time, by making small improvements and not regressing, you end up with a 5-star game or 5-star application. And so this is really a way that every team can adopt this practice. And I'll go into examples of how do you create the data and how do you adopt this. So one way to collect the raw data for non-functional testing is to instrument the application itself. There are a few really common ways to do this. One is to insert start-stop bookends to an event logging system within the application or the backend. So whenever there are key areas of the application that are being exercised, to log when they start and stop, and this can cross, for example, function boundaries or service boundaries or module boundaries on the client side, and to measure sort of the total time taken to do an action. Another way to measure non-functional data is through regularly emitted system statistics. So memory, CPU, IO statistics, rendering statistics on the client side, different statistics in terms of game engine events on the client side. By emitting these statistics regularly, you can actually join your start-stop bookends and your system statistics by time. And typically instrumentation can be left in from the testing app all the way to production, so that you can both measure this data as part of your manual functional tests, your automated functional tests, as well as your end users. So there's some really great advantages to instrumenting your app. You can get very specific to your application logic and architecture. It's very easy to get started. For example, you can just create a new API route that uploads data and then start posting to that route from your client side or your backend. The disadvantages of instrumenting your application is, besides having to change your application to add this data, is the data volume can get too much for in-app collection or production. So you might actually want to measure too much data, and that can actually overwhelm the targets in terms of how much data you want to transfer from your application, and even in production. There are also privacy issues and constraints on what you can collect in the real world environment. For example, it's very hard to get a video of application just because recording that can be difficult in some cases. It's hard to get screenshots, particularly if there's any user information involved. And so instrumenting the app does have some pitfalls in terms of you can't just upload gigabytes of data from an end user. You can't, in all cases, get the data you want. And so there's another approach to instrumenting the application, which is instrumenting the test environment itself. So when you instrument the test environment, typically you can come in from a back door to measure the data. So instead of, for example, trying to measure CPU from within the application, you can actually connect instruments, which you're familiar with as part of your development process, through special test harnesses as applications being run in the test environment. And so you can write special test harnesses that capture a bunch of different types of data as part of your manual and automated tests. You can capture the video, the frames per second, you can capture the network, the audio, system level statistics such as your CPUs and memory and GPU information, code debugger statistics such as stats on executing code or modules, and other instruments such as battery usage and energy usage, depending on what's available for the platform. So different platforms ship with different development kits. And what's really great about instrumenting the test environment is you can leverage a lot of the power that's given to you in these development kits and expose them as part of your non-functional testing. And typically this is data that's not available in the application runtime itself. And just like with instrumenting the application, you can combine data points from different systems using time. So for example, you might have several processes that are reading different data sources as part of the test harness. And you can go back in post-processing and basically combine all that data using time to give you an overall view of what was happening during that test, which you can use to make non-functional regression decisions. Another advantage of automated instrumenting the test environment, especially with automated tests, is you can really use your existing functional automated tests, which you most likely already have, and you can create more samples of data, which is great for non-functional testing because more samples means more statistically relevant results by just running those automated tests more often in more environments. So on more types of devices, more builds, more backends, more regions, you can really ramp up your data to make non-functional regression decisions by running your automated tests more frequently. And so that's really great. And one of the key advantages of instrumenting your test environment versus instrumenting your app is you can collect a ton of data this way using automated tests without worrying about the impact on the app. So you can really upload as much data as you have instruments for, because you're not bundling any of this into the application logic itself. So you're not impacting the application logic. You can also move faster because you can ask many specific questions from the data and collect data sets without having to modify the application. So really, this is a way to get around a lot of the code review and impact on the actual application. So you can start to decouple the non-functional testing from the application development itself. The downside is this is only for synthetic testing. So for your manual functional tests and your automated functional tests, this type of instrumenting the test environment does not apply to end users, and you won't be able to make non-functional testing decisions, using end user data. However, something that's really interesting is as your synthetic environment moves closer to your end users, such as using real devices on real edges, you can actually start to more closely approximate your real end users in your synthetic tests. And so this is something that at HeadSpin we really focus on, is giving customers the real edge, the real devices that they can run automated tests at scale and collect data that closely approximates the end user. So depending on your test environment, you can actually get very close to end user data in a synthetic environment and sort of get the best of both worlds. So an example of data that you can collect by instrumenting your test environments is on the right. So for example, here's a ton of instruments which are running in parallel, which are streaming data out. And then all that data is correlated by time. So we can see the game that's under test. We can see network statistics in terms of different services that are being called. We can see different time series about the video rendering statistics. And as we go down, we can see log exceptions and special messages pulled out of the logs. We can see the networking stack. We can see all the traffic going to the APIs, to the CDNs, et cetera. And we can start to highlight regions based on our definition of what we're looking for. So for example, was there a loading animation on the screen? Was there a rendering that was taking too long? We can actually start highlighting those areas to help the team start to look at areas that they think there might be risk, and starting to ask those specific questions about what do we want to measure in this raw data to help us make our application better continuously. So we've been working with this type of raw data for several years, implementing non-functional regression safety nets with our partners. And some of the lessons learned that we've seen is on how to take this raw data and ask specific questions are below. So there's been some really great effort in the community to start to define standards around non-functional testing metrics. One is called first contentful paint. It's essentially a measure of when the first data shows up on the screen. So for example, if you are in your game and you have a loading interstitial that's loading resources, first contentful paint would be essentially when the game starts rendering and everything's loaded. This is useful in a lot of ways for apps that have many transitions. For example, typically within your menuing system in a game, as you're transitioning the menu, measuring how long submenus or, especially regions that are driven by network activity, take to render, that this is a great measure. Also API performance, the time to connect to your different APIs, the time to first byte, the time to complete the API request, the connection efficiency, system performance, the frames per second, the CPU and the memory, as well as the energy usage are very interesting to look at from this raw data. Page load is a metric that we've developed at HeadSpin, which is essentially looks at how long it takes for a page to fully render using the idea of entropy. Keyframe labels is one we'll go into later into more detail, but essentially using fuzzy image matching to find keyframes and how those keyframes change test over test. This is something that's particularly useful within the gaming space to measure key user journeys through the games and how long they're taking. User perceived quality. There's been a lot of work on this in the field, especially around streaming video quality. And this is very interesting to use the raw data to measure how the user perceives the streaming quality for streaming media or streaming platforms, which is really how the encoders are coming together, and also how the CDN is working in terms of the downsampling of encoder artifacts, blockiness, et cetera. Hotspot function calls is another area in the raw data that's been very useful to look at. So how are function calls changing over time, especially key client-side function calls, whether it's parsing API results or running specific game logic functions? Are those getting worse or better, hopefully, build over build? And loading animation. So what's really great is usability has sort of keyed in on this idea that if the user is waiting for something, there should be an animation to indicate that there's some blocking activity still happening. Measuring the duration of those animations is actually very useful to quantify performance of the end user application. So whether it's video buffering or the time it takes to load the initial game, or the time it takes to load a network-driven menu or sub-menu. Those are all really interesting questions. So one example of asking a specific question from the raw data for non-functional testing is page loading. So this is an example that I've taken from an application, but opening the application, navigating to a search menu, submitting a query, waiting for the query to come back, and then the page to fully render before taking the next step in the user journey. This is a very typical type of application which goes across many types of different apps. So within a game, this would be a game nav menu system. In this case, I'm using Wikipedia as an example. And the idea is that you want to measure the time it takes to do this very common user journey, which is search for something and opening it up. And of course, if this is getting slower, that's going to be triggering our regressions. But how do you actually measure this, right? Given instrumenting the test environment. So when you look at your automated test, it's generating these black dots at the very top, which these black dots are really driving certain key events as part of your automated test. If you go one level below, there's a certain region of interest that given your automated events. So after you open up the search query, that you're interested from that point on in measuring the search result time. And you're interested, and that once you get to the next step, so you navigate away from the page that's fully loaded, that at that point the page should have been fully loaded. But if you go into the details, for example, when you actually submit the search query, how long does it take to actually enter that user event and respond? It gets very fuzzy in the automated testing world. Automated steps and automation frameworks are good at giving you these regions of interest based on these automated events, but they're actually not very precise in terms of when you queue up an event to run on the system, when does the event actually run? And so what we found is, as a good approach, is to try to separate the region of interest from the actual computed result, and using more machine learning and heuristic techniques to compute the actual result from the region of interest. So the actual result will be a sub-region of the region of interest. So if we go back here, the actual result is using sort of computer vision. At what point after you submit the query does sort of the loading begin? And at what point does the loading fully complete? And so really only by looking at sort of the data collected during that test execution can you determine the actual time. Because if you go into the automation framework, the actual steps are very fuzzy in terms of the timing. And so we call this visual analytics, where you can separate the automation steps, the region of interest, and the actual result. And really, we find that machine learning and heuristics is good at giving you the actual result versus automation, which is good at queuing up those steps to do. And so this is a really way that you can tie together the automation to the actual result that you can use to run regression. Another example is keyframe labels. So this is particularly useful for games, which have a lot of visually rich content, and you're trying to measure essentially, how long it takes to run certain user journeys within the game, which are affected by rendering performance, game engine performance, network performance in some cases. So there's a lot, if you kind of look under the hood of a user journey, there's a lot going on under there. But if we just look at the time it takes from sort of a keyframe 1 to keyframe 2 within the user journey, that metric helps us track regressions in terms of, is that user journey getting slower? So for this case, we opened our gaming app and we started a certain journey within the game. And at some point, we get to a keyframe, which indicates sort of the beginning of a certain sequence in that game. So in this case, it's opening up a treasure chest dialogue. And at some point, I tap the treasure chest dialogue to expand the treasure chest, and then the region of the game is fully expanded, and the dialogue is gone. And then what I really want to do is measure how long did it take from opening that dialogue to when I expanded the treasure chest and the items dropped out, and I began the next journey in the game. And so, very similar to the page load example, the automated test is really good at stepping through this game and tapping the buttons, tapping the elements. And the team can identify a region of interest based on those automated steps. So we know that at some point I opened up the treasure chest dialog, and then at some point I tapped the treasure chest dialog, and I began playing another journey in the game. In that region, I want the system to tell me how long it took to actually go from the dialog being open to the dialog being fully closed. And so there's another case where essentially we can use a specialty machine learning or heuristic technique to match these keyframes. So what I do is I run a manual session and I annotate out these keyframes. So for example, this is what it looks like when the treasure chest is open. This is what it should look like when it's fully closed. And I can actually tag a sub-region of that region of interest. And this is particularly useful. What we found is anytime you're doing anything based on computer vision to allow for the tagging of a sub area of interest on the screen, because you can focus on a smaller area of interest to reduce flakiness in your measurements, especially as there are background animations or sort of randomized effects happening within the game. Certain behaviors will be deterministic and testable. Certain behaviors will be randomized. And by sort of baking in this idea that you can sub-focus on an area of interest, you can, in most cases, reduce the flakiness of that sort of randomization. And this idea of using keyframes to measure these waypoints has been very useful in the gaming space in our experience. So how do you begin to approach non-functional testing as opposed to functional testing? So typically functional testing is a specific function on your development team. So you have your product engineers, your performance engineers, your data people, and your testing team. And your testing team's out there, building tests and running tests. When it comes to non-functional testing, what we've seen is that testing can be non-functional testing can be more successful when it's structured as part of a project team releasing new features or a new game rather than a specific function. So anytime a new feature is being built out or a new screen in the game or a new module in the game, you can actually adopt non-functional testing as part of that feature team and really bringing together the product engineering, the data, and the testing specialties as part of that project team allows you to build out non-functional testing questions and implement the safety net as you go. And so this is really great in terms of creating a repeatable, scalable process. What I've seen is that if you try to break out non-functional testing into its own function, it can actually be very hard to understand the baselines and implement the regression. Whereas when you create this one team as part of your project team, the product engineering prioritizes the architecture and the implementation based on non-functional metrics. The data team, as part of building the new feature, can understand how to extract measurements and test against data and run regressions for that feature. And the testing team can actually extend their test cases, both manual and automated, to include this regression testing. So a couple examples about successful implementations and types of implementations of non-functional testing for game development. So a team might look at identify CPU and frames per second as the key questions to focus on for their game development. They can set a baseline at 30 frames per second and at most 50% of a single core on a mid-level reference device, and 15 frames per second and 80% of a single core on a low-end device. And the reason the team would choose such a baseline is they're looking at the battery impact and playability for popular devices on the market. And so this is really, the team is either looking at peers or going by their own internal definition of what they want to do, but they've established the baseline and they've established specific questions about the raw data that they're collecting during their manual and automated tests to measure that baseline. And so by instrumenting the test environment, and collecting frames per second and CPU on every test, then every time they run a build and test the build, they're able to run regressions using that data, and the product engineering team can adjust the game engine and game logic as needed based on that measurement. And so this is moving the game towards overall what's considered to be an excellent baseline, and having confidence that, you know, for any device that's playing this game, that the user is going to have a great experience. Similarly for voice, any game that's including voice can also incorporate non-functional testing. A key area that's useful for voice is time to respond for voice input. So a team can look at, for every screen that enables voice input, for different voice inputs, they can set a baseline of 500 milliseconds to respond to that input. So from the time the voice is entered to the time that the game makes a response to the voice input, it should take at most 500 milliseconds. And the way to do that is to instrument the test environment to run page load analysis on the region of the voice input up to 10 seconds after the input, and measure how long it takes for the game to respond to a voice input, not whether the response is the correct response, which would be done during the functional testing, but just how long it takes to respond to the voice input. And so typically a non-functional test would be built on top of the functional test, where you get both the functional test and the non-functional metrics as part of the same test. And because this is automated, it can run many permutations of input phrases, including different locales and accent detections to make sure that everything's working correctly. And then for streaming media, so anytime there's a video breakout in a game, or streaming games or game platforms, the streaming performance is very important. Loading animations during the video on demand playback and loading, video quality during playback can be key non-functional metrics to focus on. You can set the baseline to 1 second of loading time, and the quality can be the quality that the team internally thinks is good quality. So for video quality, this is still you know, an area of evolution in the industry, but typically we've seen that if your team gets together and chooses by looking at actual real samples from your application, video quality that they think is good and video quality that they think is bad, you can use that video quality to really baseline your non-functional testing. And so you can instrument your test environment to collect video during every test, and additionally run user perception analysis on that video using either open source that's available, or a platform like HeadSpin, or other open source or research definitions of video quality to measure the video playback quality, and whether it matches the good examples or the bad examples. And so particularly reference-free quality measures, where you can just feed it really any video and it can give you a score of quality or a score of user perception, is really useful here, because you can use those reference-free scores to really baseline versus your good and bad examples. So that concludes the talk about how to implement non-functional testing to improve your game development and your backend and voice and user interface development. There are some resources out there to help your team implement automation and then start to look at non-functional testing. HeadSpin is a real synthetic edge environment and functional regression safety net. Our documentation is online at ui.headspin.io/docs. Please check it out. We list a ton of examples of non-functional testing. Also, we have HeadSpin University, which has courses on how to start automation for games. We've also been publishing to LinkedIn Learning on how to start creating automation for your games and your testing. Also, Mozilla Developer Network has some great examples on non-functional metrics such as first contentful paint. Thank you very much, and I hope you have a great rest of the GDC 2021. This has been talk on using non-functional testing to guide game, user interface, backend, and voice interface development. I'm Brian Caldwell from HeadSpin, and have a great day. Thank you. Hi, everyone. One more thing before we go. We have a little extra feature on game testing with HeadSpin. A couple nice things you can do with HeadSpin are running your manual tests via a QR code within the HeadSpin platform. So scan it on your device. You can open up your game on a local multi-touch device, and you can actually test your device on any location, hosted or on-premise, or create your own lab that HeadSpin supports. And you can run your manual testing from your hand. Another great thing about HeadSpin is the bridge, where you can use Appium and AltUnity Tester and other test frameworks with HeadSpin by using the bridge to do port forwarding and remote debugging. It's really as easy as 2 steps. The first step, just connect the remote device locally using the HS Connect CLI. And the next step is do all your port forwarding and debugging connections, and then you're good to go. So any device on the HeadSpin hosted platform on premise or create your own lab, you can connect locally and use it as a local device. Thanks for watching this feature, and hope you guys have a great week. Goodbye.